hacemos. My best achievement. Thank you very much. I want to thank the organizers, Fernando, Emil, Rafael, for the invitation. Okay, I want to talk about kind of C2 index, and I guess it is also related to the C2 index we have heard during previous talks today. I am not going to describe it in terms of a Pfaffian, but it is in fact such an invariant. I will describe the self-dual formalism where we initially studied the C2 index. Then I will describe a modest attempt we have tried to use to generalize the index so that in principle could apply to interacting systems. And then I will focus on geometric phases. Perhaps when you see this, perhaps there is no apparent connection between the first 2 points and the third one, but it is basically how we got there. So I will try to explain why we believe there is some connection between the two notions, the index being of a topological character and the geometric phase actually more of a geometric nature, but there might be some interesting relations there. So first, let me talk about my collaborator. So Javier was a postdoc at our university. Julian is a current postdoc, a current PhD student. Sebastian, Lynn, and Suad were PhD students, and Alexander and a colleague of mine in the math department. Well, I will try to give a brief overview of the topic with only these three expressions. So the first one is a expression for a projector. It appears in several instances in the context of fermions I want to describe. Well, it will be just basis projection. I am going to talk about the self-dual algebra of Araki. So we use it in order to describe the ground state of quasi-free fermions. But also in the adiabatic theorem, well, it appears as projections on eigenspaces of Hamiltonians, and in such a way it will also appear generating parallel transport for various phases. Now, something that people have been working on, mainly in the physics community, is on attempts at generalizing geometric phases for mixed states, and in particular, temperature states. So there is a work which actually appeared just 2 or 3 years after Berry's work by Uhlmann, where he gave a way of producing a lift of a path of density matrices. But only recently people have started to get really interested in that, and they have tried to use it as a way of generalizing situations at 0 temperature to situations for finite temperature. What we have done is something that comes out quite naturally from the self-adjoint, from the self-dual formalism, where we describe quasi-free states in terms of some operators that we call symbols. So H is a Hilbert space, S is a bounded operator, satisfying this inequality. It could be a projector, but if not, then the 2-point function will be defined of a fermionic system will be defined in terms of this operator. This will lead to a state, and well, we can think of it as a density matrix, something that we use to define a density matrix. Now, in Araki's formalism, when we have a projector, the state that this projector defines is a pure state. It could describe the ground state of a fermionic system. But in other cases, the state that you get using such a symbol is not a pure state. So what he proposed, as far as I know, it was Araki who proposed this idea but perhaps it goes earlier. What he proposed was to double the Hilbert space and perform an operation of this type. Here, I have written this in terms of density matrices and not of symbols, but the idea is basically the same. In the finite dimensional case, we would just take this density matrix to be a positive trace one matrix. So as you see, this receipt will generate a projection. So what we have done is basically to take this idea in the finite dimensional case, it will be possible to compute a very phase if we have a path of density matrices. So we map this path to a path of projectors. And then what we have found is that in simple examples, it will coincide with Uhlmann's algorithm. But only in very simple examples, most applications actually boil down to computing these holonomies for 2x2 matrices, even if the systems are infinite dimensional because of periodicity. But then in most other examples, the holonomies do not coincide. So we think it's a new way of generating liftings of paths of density matrices that have a nice property, which is that the zero temperature limit is always well defined for the ground state. Now, in the physics literature, there has been some discussion about the zero temperature limit because the way this Uhlmann prescription works forces one to work on a basis space, which is not, I mean, where the pure states, which are the projectors, doesn't work for the prescription. So you have to, I mean, in order to take the limit, it is problematic because the boundary does not belong to the balance, to the basis space. Okay, so this is basically what I am going to talk about.
So the zero temperature limit is when rho becomes a projection? Or?
Exactly. So you take, for instance, the exponential of minus beta, the Hamilton.
Then the thing has rho and 1 minus rho,
exactly,
which cancel out, no?
Yes. But the holonomy behaves well if you isolate, for instance, the ground state. If you have a gap and you isolate the ground state, then you will recover very space. That's which apparently in the literature for some models like heat model with long range interactions, there seems to be problems when it comes to using Uhlmann's space.
And this P rho is always a projection for any possible positive operator rho?
So what I wrote here was for a finite dimensional matrix. You just use this formula. But if you have a symbol of this type, you double the Hilbert space, the direct sum, and construct a block operator in exactly the same way. It will give a basis projection in this amplified
call it the Helmholtz projection. They call Helmholtz dilation or Helmholtz projection.
Okay. In that case, in the self-dual algebra, it will be a purification of the state. But in general, it is not a purification. Okay. So I will just recall some basic definitions. So we start with this fermionic algebra. I think this self-dual form of the matrices we saw in the last talk is a way of thinking about the self-dual algebra. So we have a fermionic system that will be described by a sister algebra generated out of a Hilbert space together with a conjugation. And it is generated by symbols B of x, which satisfy these anti-commutation relations. This is the inner product in H. Conjugation of the star operation in the algebra is defined for generators in terms of the conjugation gamma. And the map is supposed to be complex linear, so this can be also defined as a Clifford algebra and then mapped to this algebra. So this is a fermionic algebra, but it somehow is designed in order not to commit to a specific notion of vacuum. So all options are open, And in particular, this does not have the meaning of a creation operator, and this does not have the meaning of an annihilation operator. Not yet. Well, unitary operators that commute with the conjugation are called Gogolyubov transformations. The idea is that if we are given a quadratic Hamiltonian in terms of these generators, it will always be possible to find a convenient Gogolyubov transformation such that the Hamiltonian can be diagonalized. And such unitaries generate star automorphisms of the algebra. We call it S star, the self-dual algebra, which so this automorphism is defined on generators in this way. It can be extended to the whole algebra, and then we have this property which actually one could say defines the C2 index, and it works in this way. If 1 minus u is trace class, then from the fact that u and gamma commute, we can deduce this expression, so that the determinant has to be plus or minus 1. So the index will be basically taken from that component of the group of the Gogolyubov transformations. Okay, now for a self-adjoint operator, I will consider bounded operators. We can define on generators this kind of operation, which will turn out to be a derivation. And if we assume that the Hamiltonian satisfies this condition, and this was the condition that we saw earlier in the talk, so a block matrix with A, B, minus B, minus A. So this will enforce delta to become a star derivation. No? So we will have this property. This can be extended to a derivation of the full algebra. And then we come to the definition of a basis projection. So basis projections are the ones we actually use in order to describe ground states of these systems. So a basis projection is defined as a projection on H that satisfies this property. So upon conjugation, we get the orthogonal projection. That's the definition. Now, if we have a basis projection, then our Hilbert space will decompose into a direct sum of the range of the projection plus the orthogonal complement, which can be also thought as the dual. In the physics literature, this has been known. This is known as the Nambu space. So once we have a basis projection, we can decompose our generators in this way, and each one of these copies will now have the meaning of an actual annihilation or creation operator. So now thinking about cosine particles, no? These operators will generate these cosine particles. Okay, so we have this definition of a self-dual Hamiltonian is a Hamiltonian that so a self-adjoint operator satisfying this self-dual condition, and then we say that a basis projection block diagonalizes H if this condition is fulfilled. So this is a block diagonal form of the operator. Okay, now we come to the definition of bilinear elements. So I will start considering them in finite dimensions. So we consider this kind of bilinear elements given a one particle Hamiltonian H. You construct this bilinear element. But basically, what we are doing is defining derivation through this formula, and then, well, if we consider our system like formed piece by piece, so going from finite size systems to bigger ones, forming a lattice, then in the limit this will be shown to have a meaning. No? That would be a derivation, and we will get a quasi-free dynamics. In the finite case, we can easily show that this kind of derivation will give place to a dynamics, which is actually given by a second quantization matrix. So the dynamics in the one particle Hilbert space induces a dynamics in the many particle space. And then, well, so what kind of states do we have as ground states for such operators? I mean, for these quadratic elements. So ground states for these Hamiltonians will be the so-called quasi-free states. So these are basically states which are given by the 2-point function. So it's just for an odd number of operators, the value of the state is 0. Otherwise, it is given by this formula, which is basically Wick's theorem rewritten in the language of the self-dual language. Okay. So, so these quasi-free states are, as I said, uniquely defined by their 2-point correlation functions. But well, there is a more specific way of describing these states, which is that whenever we have such a state, we will be able to find an operator that we call symbol, which satisfies this identity. Notice that in case S is a projection, this is just a self-dual projection, and the state, the 2-point function, will be given by this product. No? So this is what I meant at the beginning. If we have an operator, we have a symbol that describes a thermal state, for instance. Well, we can amplify the Hilbert space and construct a basis projection in the amplified space that would be a purification of this state. And this is the way we want to propose to generate holonomies for mixed states. So, okay, once we have derivations for our algebra, we can define a state to be the ground state corresponding to that derivation. If this inequality holds, in the general case, we have to take account of the domain of the derivation. So for these bilinear Hamiltonians, the ground states satisfying this property will be quasi-free states. Okay, now if we have a Hamiltonian which is self-dual, so satisfying this identity, we can consider the spectral projections given by the restrictions to the real part, the negative part, and 0. So notice that if the system has a gap, then the positive spectral projector will be a basis projection, no? Because it satisfies these properties. No? So whenever we have a gap, the positive or negative projections will be basis projections, and those are the ones that lead to the ground state of the system. Okay, so if we have a self-dual Hamiltonian and we choose for the symbol this positive projection, then regarded as a symbol, it will describe a state which will be the ground state of the system. Now, if we choose as symbol this expression, 1 plus exponential of minus beta h inverse, where beta is the inverse temperature, this will determine a finite temperature state, which will be a KMS state. We can also consider tracial states of this form. We denote it as stress. Okay. Now, for the thermodynamic limit, I will not say much about this, but I mean, we started describing these objects in finite dimensions. If we have an infinite lattice, well, the usual form is to construct a quasi-local algebra just by considering finite sublattices of the system and constructing these finite dimensional algebras. And then the question is whether the limit of this derivation and derivations of these objects is well defined. So we will have an infinite dimensional Hilbert space corresponding to a lattice. So we work, for instance, on L2 of a lattice. We add this part in order to have a conjugation. Here I am not taking into account spin, but other degrees of freedom can be added. And then for each finite subset, we will have such a finite dimensional Hilbert space. We can construct these local algebras, take their union, and then upon completion, you get the local algebra. Under suitable assumptions, for instance, on the decay properties of the Hamiltonian, we will be able to have control on the way that these dynamics converge to the thermodynamic lead. Okay, so this is the basic context I am discussing. Now, let me come to the C2 index. Now, just as a story, I discovered this like 12 years ago. I had been interested in edge modes at the time, and I was looking for some kind of interpretation. So somehow I stumbled upon one of Araki's works, but I was disappointed but very happy because I had been studying the Shade-Stein string theorem, and in the proof I saw that there was a certain C2 index, and it caught my attention. So I said, oh, this is nice. Started working on it, and then after several months, I found the works of Araki, and I realized that that's the sort of thing I was looking for. But then I was happy. So that was the index, no? And it was very striking for me. And since then, I have not been able to stop thinking about it because the way he used it, together with Evans and other people, was in order to prove, to establish in a mathematically rigorous way the phase transition of the classical Ising model. So for me, that was astonishing, no? Because I was used at that time to hear about topology and quantum phase transitions, topology and topological insulators, but to see that there was a topological characterization of the classical Ising model for me was something quite surprising. At the time, I started to talk to colleagues from physics, and they would not believe me. Not that this was possible, but in fact, it's quite easy because, I mean, in retrospect, because the Ising model can be, of course, mapped to a quantum model, no? And then there is an equivalence between the classical system and a lower dimensional system, which is quantum, and there we have this index, no? But it was a nice thing for me to find that out. So this is more or less the way I have been trying to lead my idea. No? So try to see what could be done, perhaps not in classical systems, but for the phase transitions at finite temperature. So I will try to explain myself better in a few minutes. Okay, so first, this is some account we gave of this C2 index. The idea is, okay, we have a family of Hamiltonians. We have some idea that as long as the gap is open, I will not include any symmetries, only just consider the gap. As long as the gap is open, if we somehow are able to consider homotopy classes, then the topological character should be the same. Close the gap, something should change. So let us consider just a differentiable family of Hamiltonians, and we will assume that the gap is kept open, and we will also assume some convergence properties for the local Hamiltonians, also for the finite dimensional approximations. Now, if we take two basis projections, which are so that their difference is a Hilbert-Schmidt operator, then the intersection of the range of the first projection and the range of the orthogonal complement of the second one will be finite dimensional. Now, whether the dimension is odd or even, that will determine this C2 index. There is a relation between this and the determinant of the Bogoliubov transformations, because if we start with a fixed basis projection, well, the set of Bogoliubov transformations will act in a transitive way on the set of basis projections. So we will be able to connect two basis projections by a unitary. No? So the determinant of U will be exactly this C2 index. So this is the remark. As far as I know, it was introduced in a work by Araki and Evans in '83. And then it was used by them and other people in order to study the thermodynamic phase transition of the classical Ising model, and then it was applied to quantum systems like the XY model and so forth. Okay, so something we did was to study this index in terms of a flow of automorphisms, which is, I mean, it's not surprising, no, that we can connect the basis projection corresponding to a parameter S with the basis projection corresponding to the parameter 0, as long as the gap remains open. So there will be a unitary map performing that transformation. So what we did was to try to put this in the context of this C2 index. So let us E plus S be the positive spectral projection for the Hamiltonian HS. And then we have, well, we can consider these projections at different values. As long as the gap remains open, well, one can prove that the value of the index is 1. So this is a kind of relative index, telling us that if the gap is not closed, the index has to remain being equal to 1. So it will change sign whenever there is a gap closed. Okay, now in order to prove this, now that the value of the index doesn't change as long as the gap remains open, we use a construction which is more or less standard of this flow of automorphisms. So as I said, the idea is to construct an automorphism that maps the projection corresponding to the value S of the parameter to the initial value. No? As long as the gap remains open, everything will work. Now, the interesting thing for me is that the way of constructing this, so that I recall we have assumed that the family is differentiable, is, well, we use the resolvent identities in order to define the derivative, the projection. And, well, you know, if you have a family of projections, which somehow depends differentiably on a parameter, then by force, its derivative has to be the commutator with something. So, well, that something is written down here, but this answer is not unique. So somehow, from a geometrical point of view, that means, I mean, I am interpreting this non-uniqueness of this operator as a change of gauge. We'll try to come back to this. But in any case, the kind of differential equation one gets is this one. Then, well, you show that the derivative has to have this form. Then you solve this equation, which I will call transport equation. And then the unitaries that solve this equation will provide the automorphism we are seeing. That's the idea. Now, okay, if this unitary turns out to be commuting with the conjugation, and 1 minus b is trace class, then we can compute the index, and the index, as I said, is the determinant of that unitary operator. Now, so the problem here is to show that 1 minus b is in fact trace class, so this can be done using some estimates based on the assumptions we have on the system. Okay. Now, so I won't go into the details here, but just mention that in modern treatments, this kind of operator includes a kind of weight function that has a Fourier transform of this type. But this is not the only possibility. I will show that going back to Cato's adiabatic theorem in a few minutes. No? But in any case, the equation can be solved, and this is the solution. So this is a transport equation. It will give us a way of producing this unitary family of automorphisms, and we can get a C2 index when comparing the values of the projectors at the initial point and the final point. But this is just another way of talking about Berry phases in a way. So I will try to come to that. Now, an interlude
I have a question.
Yes.
You call this transport equation, right? But here is not related the motion pair, for example, operator, right?
The model?
Motion pair operator because it appears in transport
Yes,
equations.
I call it transport because because of the adiabatic theorem and because of parallel transport. That's something we will get in the very first case. No? So this is just an interlude. This is a part of the project that has been dormant for a while, but I think I wanted to bring it here just to see if there is a way of moving forward. No, so let me tell you about this. We want to, this index, as we have been discussing, these indices, topological quantities, can be computed when we have, for instance, quasi-free systems and we have projections. But if the system is under the action of some interactions or something like that, we will lose the projections, and we would like to have something to generalize this quantity. So what we wanted to do here was to express the C2 index, which depends on a pair of projections, in terms of states. Now, as you will see, it is quite easy to do that. But once we have a definition, one could hope, for instance, that if we work with a weakly interaction turning system, which is a perturbation of a quasi-free one, then perhaps this quantity will be stable. I don't know that, but that's something that I would like to explore. So I will tell you how we did that. So let us begin by considering the dual of the car algebra. And let us try to define something like a sesquilinear form. This is actually a pairing which is not always well defined. So we will, in some cases, or most cases, will be a divergent quantity. But in any case, let me consider the evaluation of this functional on this pair. We just pick an arbitrary orthogonal orthonormal basis for H. We evaluate this 2-point function and these two, we take the conjugate and define this as a kind of sesquilinear form. Now, it is quite easy to see that this quantity will be divergent. For instance, if we choose for this element states which correspond to basis projections. No, just plug it in here, and you will end up with a sum over the norm of all the basis elements. So it will be a divergent quantity. Nonetheless, we can do as follows. We can change a bit this definition and define another kind of pairing, which will turn out to be symmetric in the order of omega 1 and omega 2 by subtracting omega 2 from twice the trace state. And if we do that, then we can show that if the quantity is converted, then it is symmetric, and if the difference of two basis projections is Hilbert-Schmidt, then this quantity equals exactly the dimension of this intersection. So we can state the index as a quantity which depends on these two projectors. So you see, if I go back to this definition, this only uses the notion of state, so I am not using anything else. So one question that remains is, well, will this still work in the weakly interacting case? One of my collaborators, Javier Buitrago, ASA, thinks it is possible now. So this is something we started to explore some years ago. Now, it's interesting to see then that the Hilbert-Schmidt condition can be rewritten in terms of this pair. And so on, all these statements related to the Shapes time spring theorem, also to what happens when you have two projections or two states that belong to the same class, so meaning that their difference is Hilbert-Schmidt. The C2 index will determine what happens with the restriction of the GNS representation to the even subalgebra. No? And this is the way Araki established the phase transition in the case of the easy model. So everything can be just written in terms of that one. Now, I will come to geometric phases. So let me just go back to the one-dimensional theta chain, where we have this sector of the model that supports Majorana fermions and this sector which does not. Some time ago, we were playing with an equivalent version of the C2 index, not in terms of basis projections, but in terms of complex structures. And so here we had not 3 million side models, but just small ones. So just to make the point that if you consider a small system with open boundary conditions, well, the C2 index, which is this pattern invariant, well, it can be computed, but that does not have anything to do with the bulk edge correspondence. Now, if we compute it for closed boundary conditions, so I am using a parameter R to go from open boundary conditions to closed. So 0.2 is 20%, but you see the appearance of that cone already. So we were just playing around with this invariant. At the time, we found that Herman and Chris Bournet wrote a paper where they studied the infinite dimensional limit, no? And they used a similar index. Yes. Okay, now why I got interested in these Uhlmann phases? Well, in 2014, this team of Villuela, Reyes, and Martin Delgado, they did study the key type chain under finite temperature, and they computed the Uhlmann phase. How did they do it? Well, since we have periodic boundary conditions, momentum space is a circle. So what they do is they just take the Fourier transform. The Hamiltonian becomes a 2x2 matrix with values a function of the circle with values in 2x2 matrices. So there is a natural way of computing a holonomy. And they use thermal state written in that reduced space, so using the Fourier transform, and compute it. So these are the parameters of the model, and this vertical axis is temperature. Now, you see what is going on here. It is interesting. This region, if you go to t equals 0, this region is a region where the C2 invariant is -1, and here it is 1. So at 0 temperature, Uhlmann's phase recovers the Z2 index. And when you see this kind of curve and compare it with what happens in the
only integer valued?
Huh?
And how do you compute the holonomy? What's the formula? Because it's not integer valued. I thought it was.
No, it is not integer.
It's not a geometric phase.
No, it is a geometric. It is Uhlmann's phase. So that phase for density matrices. I will go to that one. It is C2 valued, no? So in principle, it is a U1 valued holonomy, but for this model, it will take values only on C2. No?
The Uhlmann phase is encoded in color, I think.
Yes. So here, the C2 index is only here. From this point to this point, it is -1, and here it is 1.
Okay.
And here, so in this region, it will be -1. Just take a cut like this. So here will be -1, and in the exterior part, +1. So when you compare to the standard picture, no, like comic picture of quantum criticality, you see, okay, if I am at 0 temperature and I have a critical point, then this is what happens, for instance, in the XY model. It has a critical point with a C2 invariant, which is -1 here, +1 here. Now, there is always like quantum critical region, but it is not sharp. No? So now, if the system displays a phase transition at finite temperature, the critical point will be the origin of this path, no? And there will be a phase transition here. So when you compare this one with this one, you say, okay, it would be very nice to find a system which displays this kind of phase transition, for which the Uhlmann phase provides a, no? But that's not the case. Why? Because the key-type chain does not have a finite temperature phase transition. For that, you will need to put interactions or go to another dimension. Things will be more complicated. I still have hope that there are models for which what we are doing really allows us to describe this kind of diagram in terms of a geometric quantity. No, but I will leave this just as a kind of insinuation of what could be done. Now I will give a brief description of Uhlmann's phase in a finite dimensional setting, which is quite easy. But I have chosen to follow an early a work by Ludwig Dabrowski and Harald Rose from '89, because I think well, for me it was more appealing, no? At least from a geometric point of view. So I will describe what is this quantum holonomy for density matrices in that language. It turns out that the parallel transport equation that you get is exactly the same as Uhlmann's. So the difference is in the way they define the bundles. So here, let us consider a finite dimensional Hilbert space. Whenever we have a density matrix, well, we can consider its spectral decomposition, and we can purify the system in the following way. So we go to the tensor product. This is different to what I did with the symbol, which was the direct sum. So here we take this tensor product and use the basis we got here, put the coefficients lambda in square roots here, and it will give a state, the restriction of which is just the original density matrix. No? So basically, if we restrict this state to the first subsystem, this state will look like the original density matrix. So it will provide us with a projection map, which is just this restriction. Well, it turns out that if I multiply with a unitary on the second factor, I will get the same. So there is a gauge structure there, which allows us to think of this as a kind of fiber bundle. Now, in order to define a connection, I will make an identification, which is not completely, so to say, clean, no, but that's the way that Rose and Dabrowski defined it. So let's take the basis space as the space of positive or invertible density matrices. No? So I will assume that all these coefficients are greater than 0. So this is a restriction. Of course, that will be problematic if I want to take the limit, because in the limit, if I want to get to the very face, the density matrix should become a projector. But in any case, we take this as basis space. As total space, we take H tensor H. The projection is just what we said, no? The restriction of the state. So this is, so to say, a section. But if we identify H tensor H star with Hilbert-Schmidt operators and ignore the complex part, we can define a notion of horizontal states. No? So this is what I mean here, saying that this leads to a generalization of very case. So what you do is the following. Just take an element in H tensor H and switch gate here, so you get a Hilbert-Schmidt operator. Of course, this identification should take into account that the isomorphism would be with the conjugate or the dual of H. But if I just keep on the like a real identification, I can define fibers, no? So the total space will be contained in the space of Hilbert-Schmidt operators, and my projection, so the gauge action will be given by the multiplication of unitaries on the Hilbert-Schmidt operators. I am talking about Hilbert-Schmidt, although I am on the finite dimensional setting, but this can, of course, be generalized to infinite dimensional Hilbert spaces. So vertical, the vertical spaces are given by the projection we define. And now here is where you can use the Riemannian part of the Hilbert-Schmidt inner product in order to define what you mean by horizontal space. So you just say, okay, a vector will be called horizontal if it is orthogonal to the vertical space with respect to this metric. So that's the way Dabrowski and Rose got Uhlmann's geometry. Once you do that, well, you work out the formula for the horizontal lift of a path of density matrices, and it's given by this transport equation. So this is why I was calling it transport equation. With a few more, a little more work, you can obtain a formula for the operator t, and here you see explicitly why the assumption that the density matrices have to be invertible, no, appears. Okay, so this is Uhlmann's formula. One example that can be computed is the classical example of a spin one-half particle going around.
In Uhlmann's formulation, you also need this to be strictly positive, lambdas, or is it just of the
no, here, I mean, in this case, because they wanted the basis manifold to be the space of like an open neighborhood, no? So they don't go to the boundary, no?
But in the Uhlmann paper, it was the same, or?
I don't remember, but I remember that they are different. They are a bit different, although the transport formula is the same. So, I mean, one can use the original one form of Uhlmann in order to get the same transport equation. That can be done. Okay. So, for instance, if we go to this spin one-half example, the equation can be explicitly solved, and the holonomy matrix will have a spectrum that behaves in this way, where temperature appears in that way. So when you take the limit, what you get is the spectrum of the, you get a holonomy operator, which is diagonal, and which has the two possible very faces as eigenvalues. No? So the zero temperature limit is well defined for this example, but beware, in the literature, people have worked with more sophisticated models, and they keep claiming that the zero temperature limit might be problematic for Uhlmann's phase. Although Uhlmann's phase actually is obtained from the trace of the holonomy matrix that can look variable. Okay, now I will run out of time, so let me just very quickly recall a basic fact about, I mean, I don't think I need to do this here, but the adiabatic theorem. No? So how do, this is the original version of the adiabatic theorem, where you enforce a slow time evolution by introducing a variable t, and then you change variables and obtain a unitary that depends on this t. No? So when you take t to be quite big, the system will evolve effectively very slowly, and this is the context where Berry made his discovery, although the discovery should be somehow assigned to Cato also, because all of his equations contain already the information, but it was not given in a geometric fashion. No? In any way, Cato's original version of the theorem states that, well, basically, if you evolve if you evolve slowly by using this parameter t, then the time evolution, the actual time evolution of the system will always belong to the instantaneous projection operator. So that was a nice thing about this theorem. But moreover, what Cato actually did was to find an exact solution to that problem. So the adiabatic theorem tells us that this holds asymptotically in T, but what he did was to find a dynamics which is exact for this relation. And this is actually an operator. You see this expression, you have the dynamical phase, and this operator, if we have a loop, will be the holonomy operator. So the spectrum will contain the Berry phases. So in that sense, it already contains Berry's phase, but of course it was not formulated in a geometric language. Anyway, what is this W that Cato discovered? Well, it is the solution of this equation, where A is this commutator. So this is what we call the transport equation. And it is not difficult to show that if we have a solution of this equation with this initial condition, the solution is unique and it satisfies this property. So it will give us this flow of automorphisms if we think of it in the context of the self-dual algebra. But you see, the formula is not the same as the one we had before. So there are possible gauges that one could use. Okay, now our proposal. Now I go back to what I was discussing at the beginning. Now let me now go back to the context of the self-dual algebra. So we are given a symbol. Now I am not assuming normalization. I am not assuming anything. Of course, I have in mind the case of a temperature state. So in that case, we have a symbol of this type. But in principle, we can apply it just whenever we have a path. Okay, we construct this projection. In the self-dual context, if we consider the self-dual algebra of H plus H, P will be a basis projection, which is just a purification of the initial state described by S. I think this is just a way of talking about thermophile dynamics, right? Now, what we propose to do is to say, okay, let me just use the natural geometry we have in spaces of projections, which is the same we use in the case of very space. So somehow we will be able to put Uhlmann's phase or an Uhlmann-like quantity and very space on the same footing. So we just consider paths of projections. Okay, so this is what we mean when we say that the autonomy of this connection will provide an alternative definition of geometric phase for thermal states. We have computed it in several cases, for instance, for different values of spin, so the same example, but not with spin 1/2, but spin 1, spin 2. And what we see is that it is only in the case of spin 1/2 that our definition coincides with Uhlmann's. And the reason is that, as we will see in a moment, is that for the spin 1/2 case, we only have two projections. In this way. But in general, we will have many more, no? So what this construction does is to isolate one part. We isolate one part we are interested in, for instance, a degeneracy space that would have any dimension, and the complement. So in this case, the very phase or the holonomy you get is of this form, and this one has to be of this form. No? But in this case, there are mixtures. No? So it is only in the spin 1/2 case that Uhlmann and our prescription do coincide. What is nice about our construction, I think, is that the limit when t goes to 0 is always well defined, because I mean, if I take this S to be a projector, well, I will get here 1, the trace will be preserved, no? And I can do all the computations just by ignoring the rest. Something which is interesting also is that there is a team from Argentina, I didn't put their names, but Courage and Reyes, they have worked for many years on the geometry of these objects on a C-star algebraic setting. So I will say something about that in 1 minute. But just to make it clear, what we are doing can be, in the finite dimensional setting, can be put in the following terms. Projections give rise to subspaces, which give rise to Grassmannians. If I pick one projection, the action of unitaries is transitive. So I can construct a principal bundle using this projection, and it will have a gauge group of this type. K and n minus k reflect the dimensions I choose for the degeneracy spaces. So k, n minus k. This will reproduce Berry's phase, or the Anandan phase also, the non-abelian phase. But it also can be used for the thermal state because we use the projection we get from the purification. Now, for a C-star algebraic approach, now this is the citation. It is a work from the 90s by Courage, Porta, and Lázaro Rey, where they start from arbitrary C-star algebras, unitary C-star algebras, and they consider spaces of idempotents, and they work out the geometry of those spaces. No? So here you pick one idempotent, and consider the orbit, this is basically what I was doing in the previous slide, you will have an isotropy group, so you get the structure of a principal bond. What is interesting is that they show that once you pick one idempotent, there is a neighborhood of that element and a local section that you can use. The explicit form of the local section is given here in this formula, and this will somehow tell you how to define horizontal spaces. No? They have a reason for their choice of horizontal space. We chose it in a way that mimics what happens here. No? So vertical space is defined by the projection, and the horizontal space, well, what we did was to consider something, no, which looks complementary to the vertical space, but which reproduces very space. So very space actually can be written in quite general terms for sister algebras, and this also works for spaces of symbols S, which can be converted to projectors. No? So this is the idea. Well, I think this is what I wanted to tell you. So thank you very much. Question.
So you said you had done examples. Can you give me just a very simple example where this temperature blow up, I mean, and gives you a non-trivial holonomy? I mean, if I start some simple system where I can do it, where this Uhlmann face or your face actually gives me something non-trivial.
Yes. Okay, let me check here. So we have computed explicitly we have computed the spin 1/2 example.
So I take one spin and I take a distribute. I mean, I'm taking a clear state, and then which path should I take?
Which path?
Yes.
Yeah. Okay. So for spin, what we did just in order to be able to compare with the standard examples was just parameterize the sphere with spherical angles and take theta to be this one, and you take a loop using this one. Okay. So in this case, so you have two projections, +1 and +- corresponding to the spectral projections of a Hamiltonian, which will be h of theta, right? Like this, no? And this is the unit vector. No? So you can compute the very phase for this one and for this one, the standard ones, as you have here. So the standard very phases corresponding to the two line bundles you get here will be exponential of I gamma plus minus, where gamma is, I think. So this is the usual hologram. If you do the computation using Uhlmann's phase, but Uhlmann's phase is actually the trace, the argument of the trace of the holonomy operator. No? So what we are doing is we don't take the trace, we compute the spectrum of the holonomy operator. And in that case, for Uhlmann, what you get is here you get a hyperbolic tangent. I have written it here. So that one. No? So you get m exponential of plus minus p mp, and m is the quantity. So when temperature goes to 0, you actually recover the cosine term. When we do it using our prescription, so we take the density. So we take now the Hamiltonian, this one, put it on a symbol which is exponential of minus h. So this is an exponential. This is a symbol. From this, we get a projection that depends on beta. and do the holonomy computation, we get exactly the same. But if we go to spin 1, then only the coincidence will be on the ground state. Only on the ground state. The other ones get mixed up. No? So now, in Uhlmann's case, for spin systems, for any value of the spin, you can use representations of the C2 to diagonalize the problem, so to say. And then in that case, Uhlmann's holonomy will give you a spectrum which gives the holonomies of all the independent line bundles for spin J. In our case, we get coincidence with the holonomy of the ground state, but in return, we get a well-defined zero temperature limit, always. Now, I am not completely sure, but in the literature, at least, some people have discussed the key-type chain with long-range interactions, and they claim, I have not done the computations, that the zero temperature limit is not well behaved for Uhlmann's phase. No? So this is a difference, but yes, so far that's what we get.
So you don't want to restrict at spin 1/2, not this 1/2 times c, because you need this gamma c.
Can you repeat the question, please?
So if you have spin 1,
Yes.
can you enforce this self-duality?
No, that's different because perhaps I was not clear enough, but so to say, our idea came from working with the self-dual formalism. But then we said, okay, if I have just a random density matrix, I just
You can
take this projector and I can compute my very phase. No? Now, the difference is that if you are in the self-dual formalism, of course, you could add spin. No, I don't know what the result would be, but we would still have a self-dual algebra. And in that case, for any symbol, we can make the construction of the corresponding projector, and that will give rise to a purification of that state. Now, this formula for the projector will not give a purification in the general case, only in the, I mean, for sure, it is a purification in the self-dual context.
One more question? Comment?
It is possible to use this Uhlmann phase to approximate the shared number, for example, positive step. I don't know, maybe for the Haldane model.
Yes.
or maybe the thermal transfer.
I mean, perhaps, but I mean, I am stuck with this C2 phase because of my. There is something. I mean, I need to be able to get something with that diagram. No? I have two ideas. No? One of them is, for instance, doing something like mean field computation. So set up a model, which is an interacting model, set up a mean field approximation. Now the coefficients will depend on temperature. It might be possible that this index gives additional information. If I do it just for a random quasi-free model, the projection, the extended projection will give no information that depends on the temperature, because it's just an exponential of minus beta h, doesn't do anything. But if the parameters of the Hamiltonian depend on t, maybe there is a way. But yes, you're right. I don't know. It would be nice to explore that in that context.
Well, any other question? Comment? Not Andres, thank you very much. Sorry. Not clap.
So, if you're adding back parameter here, which is the azimuthal angle, right? I replace that by k of a one-dimensional crystal. What these phases would be in the, not in the mixed case, but in the pure case, I guess, those would be the displacement of the one-year centers within the crystal.
So you mean like a momentum variable, or?
Yeah, if your holonomy is going across the Brillouin zone in a one-dimensional system, those phases there
Yes.
would be at least, not in your formulation, but in the typical, very base calculation.
Yes.
That amounts to a displacement of the one-year centers.
Yes,
with your crystal.
So if I understand correctly, what you are posing is here I have translational invariance. Let us take periodic boundary conditions or just an infinite system. Actually, we would have to take an infinite system so that k is a continuous variable. No? So the region sum would be a circle.
Yes.
Okay. What people do is they express this as a like a direct integral of operators, which are, let's say, of the form hk. But these hk's, they are of this form,
right?
Because there are no internal symmetries or more. So what you end up doing is, even if this is an infinite large system, or yes, then what people, I mean, at least what Villuela did was to compute the holonomy while you go across all the real samples. And what they get is this fancy picture. The problem, they were very good at advertising it, no? But this has no physical meaning whatsoever. No meaning.
Sorry, is this for the trace of the holonomy already, or?
Yes, they take
Yeah, yeah. But my claim is that if instead of taking the holonomy, you take the eigenvalues, as you did in your slide, right? You keep the two eigenvalues.
Yes.
Then that should inform, the displacement of the one-year centers with the one crystal.
Yes.
At least that's the case, if I think of a non-interacting system as a usual connection to.
Yes, and this is a nice way of seeing how you land back on Berry's face, no? Because if you plot this, I mean, just you see on the dependence on temperature of M. No? So, but and in fact, what you're saying is I mean, if you think of this as a winding number, then it will encircle the origin or not, and depending on that, you will get a trivial or a non-trivial winding number. No?
Yes.
That will still happen, and this is why here you get -1 in this region, and from here on you will get +1. But the problem is that, at least for this model, this has no physical meaning. No, unfortunately, no. But what I am trying to do is to figure out a way of coming up with a mean field approximation, where this plot reflects something of this sort. That would be very nice for me, but so far, no luck.